Let me. Okay. Uh, so yeah, we can start. So my name is Firdavs Rakhmonov. I'm currently a postdoc at the University of St. Andrews. I got my PhD a year ago at the University of Rochester under the guidance of Alex Yosevich and Kaveh Hosseini. So I will talk about uh, orthogonal projections in finite fields and Fourier analysis, discrete Fourier analysis, and a bit about incidence geometry. So this is a joint work with my mentor, Jonathan Fraser, and this is actually logical continuation of his talk, which he delivered earlier today. So this is the content of my talk. So let me start with the introduction. So let me give you some motivation. So Marshall theorem is the fundamental result in fractal geometry. It was proved in 1954 by Marshall, and it says that if we take E, which is a Borel set in Rn of this Hausdorff dimension, then the Hausdorff dimension of orthogonal projection of this set onto almost all k-dimensional subspace is equal to this value. So this bound was proved by Paris and Schlag, Paris and Schlag. And so it actually estimates the Hausdorff dimension of exceptional set. So what is the exceptional set? Exceptional set is basically the set of k-dimensional subspaces whose for which Hausdorff dimension of orthogonal projection is small. And the upper bound is given by kn minus k, which is dimension of Grassmannian, gkn, which is basically the number of k-dimensional subspaces, not the number, but the collection of k-dimensional subspaces, and plus this term. And I will talk about finite field setting of this problem. Many problems from geometric measure theory was considered in finite field setting. The most famous example, there are many examples, such as Tekea problem, which was solved by Dvir and Josevich-Rudnev problem about distances, and all these results are they became very influential. So the main object we are working with is the finite field. So once we have a finite field, we can consider finite dimensional vector space over this finite field. So the finite field analog of that bound is this. So we would like to estimate the exceptional set in this way. So again, what is the exceptional set? Is basically the set of all k-dimensional subspaces for which orthogonal projection is small. And here, q to the kn minus k is basically the size of the Grassmannian. I will talk about, I will give more details later. So this is the finite field analog of Marshall projection theorem in finite fields. So Chen established this result in the case of prime fields. So our main result is improvement of that bound, which takes into account LP properties of the Fourier transform. So our argument consists of two key steps. So the first one is establishing a certain character sum associated with subspaces. And the second one, we prove an analog of Plancherel's theorem for subspaces. And it's interesting in its own because it turns out that it generalizes certain moment identities for incidences due to Murphy, Petridis, and Chen. So first of all, we need to define the Fourier analysis in FQN because this is our main tool. So once we have a function, complex valued function defined on FQN, we can define its Fourier transform, and the Fourier transform is defined in this way. So in the definition, of the Fourier transform, I'm going to consider normalized. I'm going to normalize it. So I have to divide it by the size of the space, which is q to the n, and chi should be is a non-trivial additive character. So the choice of this chi is doesn't play any role in what follows, and the following result is very important, and it's called Plancherel's theorem, and it connects the L2 norm of the function with the L2 norm of the Fourier transform. So now I have to introduce the next combinatorial object, which is known as Gaussian binomial coefficient. So it actually, in some sense, generalizes the standard Gaussian binomial coefficient and is defined in the following way. So suppose we have three parameters, kn are non-negative integers, and let's take q to be power of prime, then Gaussian binomial coefficient is defined when k is at most n, it's defined as this product, and when k is larger than n, it's defined to be 0. So it's easy to observe that when k is equal to 0, so this product is equal to 1 because we get an empty product, which is by convention is equal to 1. And so I already mentioned what is a GKN. So let's do it formally. So GKN is basically the set of all k-dimensional linear subspaces of FQN, which is in this case is a finite set, obviously. And it turns out that there is an interesting relation between this Grassmannian and the Gaussian binomial coefficient. It turns out that the size of this Grassmannian is exactly binomial coefficient n choose k with base q. Actually, there are many other identities which relates Grassmannian and Gaussian binomial coefficient, and many of them they have been used in the proof of our main result. So now we have to define some framework which captures the Fourier analytic behavior of a set, and it was done in the work of Fraser. First of all, we need to define the P norm of the Fourier transform. So if E is a subset and P is some number from 1 to infinity, the P norm is defined in this way. So it's basically it's a normalized sum of non-trivial Fourier coefficients. Because of some technical reasons, we are going to exclude trivial Fourier coefficient. And Jonathan, he already mentioned the motivation of the notion of PS Salem set. So I'm not going to do it. I'll give just the definition. So once we have a subset of FQN and we have two parameters, P and S, we say that E is a PS Salem set when the P norm of the Fourier transform has this decay. And the usual notion of Salem set, which was introduced in the paper of Josevich and Rudnev, is basically when you take P to be infinity and S is equal 1 over 2. Of course, here I define the P norm when P is finite, but you can do this for infinite. For infinite, you just have to, you just need to take the maximum of non-trivial Fourier coefficient. And in particular, you can see that any set is a 2 1 over 2 Salem set, which follows trivially from Plancherel's identity. And also in the paper of Fraser, it was shown and every set is a P 1 over P Salem set for every P is at least 2, which is also pretty very interesting result. So now we have to define the projection. Uh, we have to define projection in finite fields in a slightly different way because of some subtleties between FQN and Rn. So if E is a subset of FQN and V is a subspace, so the projection of E onto V is basically the set of all cosets of V perp such that it intersects E. So V perp is uh, is the orthogonal complement to V. So it's easy to see that we have this upper bound for the size of uh, projection, and we are interested in estimating this the size of this set. So what is this? This is actually it's called exceptional set. It's the set of all elements of Grassmannian. So basically, it's the set of all k-dimensional subspaces for which uh, orthogonal projection of E onto this subspace is small. And here U is a positive parameter, but the case of interest when U is small. So namely when U is less than this uh, value, which is minimum between Q to the K and E, because otherwise it's easy to show that the size of the exceptional set is equal to the size of Grassmannian, and we know that this is Q to the K and minus K because Gaussian binomial coefficient is a polynomial of degree Q to the K and polynomial of degree Q K to the N minus K. Okay, so our main result is the following. So if we have two parameters, P from 2 to plus infinity and S between 0 and 1, and E is a non-empty PS Salem set, and U is small, then the size of the exceptional set is at most this. And here, Q to the K n minus K is the size of the Grassmannian. So we have this result. So this result, it depends on two parameters, P and S. So it gives us some flexibility. So it gives us some flexibility. And this theorem can be considered as a finite field analog of a result by Fraser and Orejana. And they consider the continuous case. However, in their result, they don't have this kind of constraint between U and P, because in our case, in finite field setting, it arises when we consider the origin. And usually when the origin plays an important role. However, in the continuous case, we can ignore it. And as I said, our result depends on two parameters, P and S, and taking P to be 2 and S to be 1 over 2, we obtain this one because any set is a 2 1 over 2 Salem set, which follows directly from Plancherel's inequality. So we obtain, in particular, we obtain this result, which is Martian theorem in full generality in finite fields. And in particular, when U is small, we can show that the size of the exceptional set is a little o of the size of the Grassmannian. So as I said, the proof of the main result has two key steps, and the first step is the establishing certain character sum. So this result was proved. The particular case of this result when the ground field is prime was proved in the paper of Chen, but he conjectured that this should be probably also true for arbitrary fields. And this was done in our paper. So it turns out if you take any U which has dimension n minus k and x not in U, then this character sum over all elements of U perp is 0, provided that chi is a non-trivial additive character. And the second key step is Plancherel's theorem for subspaces. But before I formulate theorem, I have to give some preliminary, which is pretty easy. So if U is an element of Grassmannian n minus k n, which means that dimension of U is n minus k, then it's easy to show that the number of cosets of U in FQN is exactly q to the k. So we can write this cosets in this way, as this collection. And the second one, the second notation is this. So if we have a complex valued function defined on whole FQN and A is a subset of FQN, we can define this sum of function over A. So I'm going to denote this by S sub FA. It's like L1 norm. Of course, it's not L1 norm, but and the Plancherel theorem for subspaces can be formulated in this way. If you take U to be n minus k dimensional subspace of FQN, then for any function defined on FQN, we have the following identity. So on the left-hand side, we have the L2 norm of the function over subspace. On the right-hand side, we have this sum. And in particular, it generalizes Plancherel's theorem if we take U to be trivial space, because if U is a trivial space, then U perp is obviously the whole space FQN. And on the right-hand side, you will get q to the minus n L2 norm of the function. And the last section of my talk, it's about incidences. It turns out that the notion of LP averages in finite fields has some nice application, and during this project we were able to find this very interesting application. So, and it turns out that you can apply it to prove to provide a new proof of some result. But first of all, we have to define what is AKN. So AKN is basically the collection of all k-dimensional planes in FQN. So the second one is a incidence function. So if we have a point set in FQN and we have some k planes, so we can define incidence function in this way. Is basically is the size of this set, and this set is basically all possible pairs point plane where point belongs to the plane. And we're going to define this notion of moment. Moment of point set over k planes, and it's this is the motivation why we call it moment. Of course, it depends on parameter r. So Murphy and Petridis, they computed the exact value when k is equal n minus 1. Basically, they computed the second moment of the point set over hyperplanes. So we were able to generalize this result, their result for all k planes. The most interesting case here, of course, the second moment, but in order to make the result self-contained, I also added the first two, computing the zero moment, and the first one is easy. the zero moment is basically the size of the AKN, the size of K planes, which is equal to this. And I would say the most non-trivial here is the second moment, and the proof of this actually reduces to the uh, uh, to the result which I mentioned before, namely Plancherel theorem on subspaces. But Plancherel theorem on subspaces actually relies on the character sum, which I also mentioned. So Wien established, so probably the most famous result in incidence geometry is the Semeredi Trotter, and Wien established the finite field analog. So he proves that if we have a point set in FQ2 and we have a set of lines in FQ2, then we can give an upper bound for the number of incidences in this way. And also he proved the high dimensional version of this, the number of incidences between point set and hyperplanes. However, if you compare these results in the high dimensional, he has extra factor 1 plus little o of 1, which is missing in the two-dimensional. And a natural generalization would be to consider the collection of K planes. And the following result was obtained independently by Lund, Saraf, and Bennett, Josevich, and Pakianaton. So they obtained this upper bound for the number of incidences between point set and K planes. So it turns out that this result was proved by Hammers in 1980s, but for some reason it was lost. And I want to notice that all these results which I mentioned, they rely on spectral graph theory. And we, in our joint paper with Fraser, we proved this result. Of course, I want to stress out that this result is not new. As I said, it was done already, but to the best of our knowledge, our proof is new. It uses basic Fourier analysis and simple combinatorics. And also, the expression inside the larger brackets is bounded above by 1 plus little o of 1. Several useful consequences follow from this result. First of all, this theorem quantifies 1 plus little o of 1. And also, if you, so again, this is not new. The factor 1 plus little o of 1 also follows from result of Hammers, Lanz, and Josevich, Bennett, Pakianaton. I just want to stress out that the proof, to the best of our knowledge, is new. And one of the first questions we asked ourselves was whether this 1 plus little o of 1 factor is actually necessary, because it doesn't appear in Vin's result in two-dimensional case. And it turns out that in some cases you can remove 1 plus little o of 1, for example, in the case of hyperplanes, or when the size of E is large, namely the size of E over Q to the n minus 1 goes to infinity. So in this case, you can actually remove this 1 plus little o of 1, and it improves Vin's high dimensional result. I guess it's a good point to stop, and I want to thank everyone for the attention.
Thank you, Firdavs. We do have time for a question, if there is a question. If not, we thank our